here. As I was saying earlier, we have 14 problems to kind of go through today. Uh, right next to the problems as we go through them is the answer. I encourage you not to look at the answer. It is really easy to just look at the answer and go, oh yeah, that's right, I know that. That's not the point of the review. The point of the review is to test what you do and don't know so that you know what to go back and study. Um, it was very tempting for me. Some of this stuff we haven't touched in almost a couple of months. So it was, for me, it was a bit of dusting off as well. So, all righty. Let's, also, as I was saying earlier, this is also your time. This really isn't, this isn't, I can espouse for the whole time, that's fine. But first of all, I think that would be boring. And two, would be counterproductive to what we're trying to achieve today, which is review the subject matters that you need review on. So speak up and participate and let me know what's going on there. So, it looks like most of you have the ones that have answered 3 or 4 exams coming up. So hopefully, if this one isn't a huge time sink for you, but I don't know, we'll see. If you want to go into breakout rooms, that's fine, but I probably think no, unless you have a strong opinion about wanting to be in breakout rooms. I don't know how many people are going to show up. We've got about half the class here. So for now, I'll start without breakout rooms. And let's look at
where is the, I'm not seeing the module for this assignment.
You're not.
No.
Oh, that's always a bad start.
Not sure if it got published.
Same here.
I tried refreshing it.
Of course. Now look. Hopefully that will do it.
Oh yeah.
Thank you.
There we go.
It's interesting. You have to publish it in 2 locations. You can't just publish it in 1. I seem to forget the primary. All righty. So the first couple of slides are just kind of reminders. I mean, this very first slide is just saying, hey, this is the basics of statics. This is that all the forces need to sum to 0. These are the basis of our equilibrium equations. You need to, of course, remember that. I'm not going to go through this page here, which is 7-2. Again, that is all sort of the basics. We'll do a couple of questions that will kind of reinforce that, but this is the reason I really don't want to go through this is that the notation is probably somewhat different than what Joanne and I have used, and to go through that notation might just be more confusing. If it helps you to see a second set of notations, formats, that's great, but I would think not. So this is, again, we talked about in the very beginning of the class, we talked about different ways to represent a vector in components, magnitude and unit vector, and also direction angles and magnitude. One of the things that they talk about a lot is the line of action, which is anything along that unit vector that has the same unit vector really will be along that line of action. And so we actually use that a lot later on and talk about line of actions, whether they are parallel, perpendicular, or whether they're all concurrent, i.e. intersect. And I'm not going to go through that. Let's go right to the questions. So the answer is on the second page. A rigid body is in static equilibrium experiences. We got 4 answers there. Anybody want to venture forth what they think the answer is?
D.
What was that? B?
D.
D. No unbalanced forces, of course. So the whole idea is that equilibrium, they're all balanced. So some of the language is going to change a little bit. So be on guard. um, is what I have to say about that. Normally we would say, you know, all the forces are in equilibrium. That would be the way we would say that in this course. Some of the language in some of these problems, because some of these problems have been stolen and, you know, liberally from other sources. Sometimes some of the language is a little weird. So particularly like in this problem, generally I try and clean up language on the problem so that it's consistent with what's been presented to date for you guys. So the next one, all the following characteristics of force except, and again, this is a force, not a moment. So again, it's important to read this correctly. So of those four, which one is the one that doesn't belong? You know, as they love to say in preschool, which one of these doesn't belong? I think there's a little song on Sesame Street. Anybody have any ideas?
Is this also D?
Yeah, D, the center rotation. That would be for a moment. So all of those things there. Again, the line of action is kind of an important thing about a force to remember, along with the direction and the magnitude.
How is line of action different from direction?
That is a good question, and I honestly
Back from the
don't know if I
tail,
can-
it's like behind it.
Yeah, there you go. Line of action could go both forward and backwards. It can go anywhere along.
Well, line of action also implies a displacement. Whereas direction could be a unit vector.
Yes, direction is a unit vector. So
Whereas line of action actually has like a displacement from the origin. It has a.
yeah, so we
it's like
might have
It's like the slope, the difference between a slope and a line equation.
Yeah. right there. And so we could have as Jason was pointing out, we could have you know, X, Y, and Z unit vector there components, but we have to know that it intersects here. And then the line of action is anything that goes along, basically is concurrent and parallel to that force.
And the direction is defined differently in what way specifically?
Hold on a second.
And I'm kind of curious what the specific, I'm trying to understand what the specific like I can kind of feel the difference, but I'm trying to understand like what the actual definition difference is.
UE would be, you know, I, J, and K, and A, B, and C, such that A squared plus B squared plus C squared is going to be equal to 1. A, B,
So
and C.
the direction is defined as a specific unit vector, and the line of action has a location relative to the origin, whereas the unit vector doesn't necessarily, correct?
Well, it all depends on where you define the origin, because you could also look at the direction as direction angles.
Yeah, but
Yes,
what matters is that
relative to this spot right here. So as we were talking about, relative to the tail. So the direction is relative to the tail. So I'm going to struggle a little bit today too, because this is, like I said, going back a little bit. I didn't prep this, have as much time to prep as I would like. So You guys are doing great. We're doing great so far.
Yeah,
Keep
you're doing
asking
great,
me.
Rob.
Make me struggle. Well, that's good because you'll see me hopefully get to the correct answer eventually, which is what kind of exams is like. Back to sharing the screen. And there's the answers. All right. And try and keep that off of the screen there. The answer. So this one's asking you to basically come up with a magnitude for those three components being put into one vector, or three vectors, if you will, that each have only component in each direction. Depends how you want to state it. And so they've given you the form of how the answer is supposed to go. Hopefully, at this point, all that is fairly straightforward for you. That basically, you would take these three components and put them into this equation and come up with a magnitude, 4, 5, and 3. I believe the answer is C. You use your calculator. No. And again, if you don't understand this principle, this is, I think it's the Pythagorean theorem at work here. All right. This one, hold on a second. Block off part of the screen there so we don't get the answer. So this one's again asking you to provide the resultant of all of these components added together, and the magnitude, just the magnitude. They're not asking for direction. So, what would be the best way to go about this? Anybody have any thoughts?
You could break each one up into individual components for each force, but how they conveniently might have shown it right off to the right there with just doing all the X's at once and all the Y's at once seems to make a lot more sense for this type of problem.
Yeah. Yeah. So if I were to do this, I mean, clearly this one and this one are, this is X only and Y only, but these you would want to break it into the forces, each one of them. You know, again, and so then you would just add this, this, and this, and then for the, I lost my blue one. There it is. For Y, this, this, this. Yep. So, and you know the angles. And so life is pretty straightforward. Of course, Joanne and I kind of insisted that when you're doing the sum of the forces in the Y, that what you do is you use the cosine from the Y axis, X and Y. So you would do the cosine of this angle and the cosine of this angle and the cosine of this angle. You'll see that in their definition, I believe, if I go back to theirs, they use the sine when they're using the Y, and they're using it from the X axis. So hopefully you use the cosine from the Y axis. Again, the reason that we kind of did that in all this time is that there's less chances for errors in negative and positive senses. So you have to be somewhat aware of that. You'll see that they did sine of 120 degrees rather than sine of, anyways, you just have to be careful, is my point. Some people might be tempted to use the sine of 30 rather than the sine of 120. Okay. Just be mindful of that. This is just a review of how to do moments with the right-hand rule, basically. And the only thing that I really wanted to point out to you here was this is what was taught in the book, is that it is the moment times, excuse me, the moment is equal to the distance r crossed with the force. And then they go down and they do that. And they choose to figure out what the length of r is in the perpendicular. And I taught you guys a second way in one of the labs as to how to do that. And I'm going to go to my board. So if we have x and y, and here's our force, and here's our point where we want to do the moment. We're going to do the moment about A. What they want you to do is to calculate that distance r rather than, so there's one way. This would be r, and this would be f, so we would have r times f. And the alternative way to do that, I'm trying to remember how I do it in this particular case. It might be easier to do the component of f this way. So this becomes r, and that's f. Both of them will result in the same answer. This is how you taught it, is taught, which is that you get the perpendicular. Here you're creating another perpendicular, but this is some component fx, whereas this is some perpendicular. So we would break f into x and y, just different. Sometimes this is going to be more expedient, as it was in our lab. But this is the classic definition. And of course, because it's a cross product, or the order with which you do these equations is important. And you'll note in this definition here, again, they use the sign. Anyways, you would find that if you did this both ways, that this equation right here, where the moment is r times the magnitude of the r times the magnitude of the force times sine of theta, will end up being the same. That equation will be identical in both methods. It's just a matter of how you choose it to do it. All right. This is about couples. My question that I always have for people about couples is, does the moment change anywhere on this plate?
No.
No. And that's the most important thing to remember about couples, is that no matter where you go, so it doesn't matter where you calculate the moment for this couple. So if you were to calculate, here they've got the origin right in the middle, it means that in essence, you have to do two calculations. You could have easily have chosen to do the moment anywhere along the line of action of one of those forces and then only had to do F times D rather than F times D over 2 plus F times D over 2. So just saves you a little bit of effort. I'm not going to go into this. This again is equilibrium requirements, basically saying that the sum of the reactions or the sum of the forces is equal to 0 and the sum of the moments is 0. All right, here's the problem. The moment is due applied to the moment due to an applied force on the body is 0 only when force is negative, the force is through the origin, the line of action passes through the center of rotation, the force is a function of time. So this is a classic case that some of these you can immediately eliminate. Clearly, it's not a function of time. We've never talked about time anywhere in this class. Anybody venture a guess on this one?
I think they want C.
See, yeah, so the line of action through the center of rotation. So it means that, again, the center of rotation is kind of thing I probably would have said center of gravity. But anytime it goes through the center of wherever you're taking the moment, the answer is there is no moment. So basically the force is concurrent with the point that you're trying to take the moment about or calculate the moment about. So yeah, the answer is C. So this is about notation. What is the correct way to notate a moment? And anybody have any thoughts on this? Clearly, I don't know if you know what that upside down triangle is. That is what's called the gradient. That is basically the instantaneous derivative of a function at any point. So that's called the gradient, which is why when you talk about going up a hill in a car, it's called the grade. At any point, you're basically taking the slope of the surface that you're on. So that's why it's called the grade. Anyways, this is the gradient. Clearly B and D, since you're using gradients, is not part of this. So it really boils down to, is the moment a dot product or a cross product? And the cross product is the correct answer because the dot product provides you with a scalar answer and a moment is a vector. All right, a couple is composed of a pair of forces that are, and I'll let you guys read that and tell me what you think the answer is. So somebody was guessing, I think we're on C here, equal, opposite, and parallel. That is correct. So they have to be equal in order to be a couple. So the first two, just by the fact that they're unequal, means that you can eliminate those. So it really boils down to, is it C or D? And we know that they're equal. They do have to be parallel, and they only become a couple when they're opposite. So they have to be equal, opposite, and parallel. Here we actually have a real bona fide problem. I don't, just so you know, I don't think there's a lot of those types of questions where it's about verbiage and definitions, as we just sort of went through. There'll be some of that, but that's not going to be a heavy leaning on the questions. the assumption is that you sort of know that. Those, I look at those definition questions usually as what I call give me questions, which is sort of the, you get to have a couple that you absolutely will get right. And then harder questions further on. So if there are any of those, hopefully those are give me's for you that you just can look at them and answer them quickly and save time and move on and get correctly. So this next one, I'm going to cover up the answer on my. You better determine the magnitude of the moment of the force about the corner A. So before we go any further, before we answer this, is this problem going to be static?
No, there's only one force.
Yeah, yeah. And it's going to create a moment about A, which we know, and we know that pins can't resist moments. So the answer is this is unstable. They're asking you to calculate the moment at point A, but it is not a stable. So you wouldn't be able to solve for the reactions in this problem. So this would be indeterminate. So how would we go about doing that? Let me
I mean, we see it, but it's like break the force into components, and then each component has a moment around A with the perpendicular distance. So
yeah,
the X component will have that height 8 as its distance, and the vertical component will have the horizontal distance, the 12.
yep. So you'll have to create equations for two moments to sum up. Just to summarize what you said, David, we've got our box. We've got a force. And what we're doing is we're doing Fx, Fy, this is A, and we're doing sum of the moments at A. It's going to be, excuse me, let me write it in the correct order. It's going to be Y and X, and so we're going to do X cross Fy plus Y cross Fx. And notice that X and Y and X. So you wouldn't do X times Fx because you have X and X. You want to have them, they can't be the same orientation, same axis. Going back to that, the answer is D, and they've done that as well. And then we thought stuff with Locker. So this one kind of is a little annoying for me. I don't, a lot of these problems sometimes don't have numbers in them. If you're anything like me, I kind of like to see numbers, but sometimes it's useful to just go through the whole equation without any numbers in it. The cube, let me prepare that. Cube the side of length A, so it's basically A by A by A, has a force acting on it, and they don't make it very clear that the force F, they kind of do, is in the XY plane, or I should say the XZ plane. It's asking you to take a moment about the line AB. Does anybody remember what the procedure is to get a moment about a line?
Yeah, we should find a moment about a point on the line and then dot that with the unit vector of the line.
Absolutely correct, Jason. Yeah, so as Jason just said, find the moment about any point on the line, and then dot product it with the unit vector of the line, and you'll come up with the same answer no matter where you take that moment on that line. And you'll notice that the answers are only in scalar form. There is no vector form. So if you saw an answer with a vector form in this question, you would immediately know that that is wrong. So, and that's basically what they do here. Again, their notation kind of makes me bleary-eyed. I wouldn't have done it quite like that, but again, there it is. So, and like I said, they don't tell you very well in this equation that the force vector is only in the x and z plane. They sort of infer that with that funny little line. That would be one of the questions that if I saw this on an exam, I would ask the instructor, what is going on here? So if you see that kind of thing and you're unsure, definitely ask. I will be proctoring the exam next Friday. So feel free to ask me that question or that kind of question.
Oh, do we have to log into a Zoom when we take the exam?
I'm not quite sure how Joanne wanted me to do the proctoring. The answer is it's going to be synchronous. I think you'll be able to use the Zoom whenever you need it. So yeah, we may be logging in.
Okay.
So it's mostly for your benefit. Again, that's what she asked me to do, and I'm happy to do that. But so we want everybody to take the exam at the same time.
There is a Zoom listed on ConferZoom that's new, although it's for Thursday. It's not. Right.
There are some students that have a meeting on Friday morning for, I think it's engineers abroad. I'm trying to remember what we discussed. So there is some differences there. I think there's 4 or 5 students who will be taking it Thursday evening.
Okay.
And everybody else will be taking it Friday morning. So,
Is that, what time is that at, Rob? Is that 8 o'clock normal time?
no, it's 9 o'clock on Friday. You get a little extra sleep.
Okay.
That's when the exam is scheduled.
So it's 9 to noon.
9 to noon. And
Okay.
with accommodations, you get a slightly longer time.
Okay. Cool.
Rob, could we actually go over that one on the board? That one kind of gave me a little bit of trouble.
This one here, yeah.
Yeah.
Like I said, it kind of made me bleary-eyed too. So let me stop sharing and put it up on the. Have I got you guys on the board yet, or am I still looking at me?
We see your face.
Here. There we go.
There we go.
So let's see how well I can draw. And they went, I'm going to do it as X, Y, and Z rather than I, J, and K. It almost looks like this was done by a physics guy. And so they've got a vector, or I should say a line. This is what they're going to call A, and this is B. And then we have a force. Actually, it doesn't end there, sorry. It does not intersect point B. And if anything, it's probably over here, F. So when I look at this problem, for me, I would probably want to take the moment about A and call A the origin. So F, let's define F first. It goes, like I said, it has no Y component. So we have X as you're looking at F straight down. This is a 45-degree angle across. So you could say, this would be how I would do it. I would do cosine of 45 degrees times F in I, and I would say that's a negative. It's going this way. And then, of course, like I said, there is no Y. So then I would say it is cosine of 45 F J. So that would be how I would describe that vector. And then I would take the moment about A.
Cosine 45 FK.
Yes, sorry, thank you. That would be how I would do that, would be, I've lost my blue pen. So then I would take the moment about A. So it would be R cross F. And because I am terrible, we could do this in two ways. We could do this by the right-hand rule, or we can do it by just putting it into a matrix. My preference typically would be to do it by the right-hand rule. And so that would be our first, let's do the sum of the, we do the about Y, we would have, so we're not going to have any moment about which axis are we not going to have a moment about? We have a moment about all of them, aren't we? All right, so the moment about X, well, let's do it the other way then. Let's go. We have I, J, and K. And what is R? It is A. And then J is A, right? And then K is 0. And then we have cosine of 45 F, and then 0, and then the cosine of 45 and F, and then we evaluate that. So for me, I get A times cosine 45 F. So that is this way. This next one is going to be 0. And then the next one is going to be also 0, correct? We're going to have 0 and 0 here. So then the next set going the other way. Is going to be minus A cosine 45F. See if I'm doing this right, guys. It'll be interesting. And
I mean, you gotta rewrite 2 columns in order to do it that way.
yeah, I'm just kind of, I'm doing it in my head.
Yeah,
And that's why I said, see if I'm right. I'm running out of space.
that's hard to tell.
So then that, again, the second one's going to be this one, because the other, this column will go over here. That's going to be minus A, again, cosine 45F. And then the next one is going to be, because there's a 0, right? So a 0. So and I think we end up with A cosine 45, right? F. I got that right? Something seemed funky.
Rob, isn't each of those, you need to put an I, a J, and a K on
Yes, thank you.
each of those? And then the,
So this one is I right here. Excuse me, I. Yeah, that was I. J is 0. K. K would be A.
I think
times-
your second term is J and then your third term is K.
No, this is J
But
here.
I think your third term should be positive.
Okay, I'm going with it.
Someone else could check me on that, but
Anyway, so that's, you end up with your vector F. Excuse me, your moment. And the unit vector of this, the hard part is getting F, is getting the moment, and then getting the unit vector. Unit vector is going to be A squared plus A squared plus A squared, right? That's the magnitude. So that's how they got the 1/3 A squared. I should say square root of, yeah, square root. So, and eventually it becomes, you would have A squared over A squared square root. They cancel out. I,
Your unit vector should just be A root 3.
yeah, as I say, the A squareds go away.
That'd be
J.
changed. Okay.
And K, right? Which is what they've got for that. So this is the hardest part right here. And like I said, I'm not really happy with the way that worked out. Might be easier to have done this the right-hand rule, which would be Y, we get 1, X, we get 1, and we get all 3 here. So if we were to do it that way, let's do Y first. Let's do the moment about the Y. That's going to be 45 of that is this way, and it's going to be new negative. It's going to be a negative. It's going to be cosine of 45 A times cosine of 45F. Moment about our X is going to be, again, Y. So this is F. If I wanted to do this, I'd do F. I have A, Y. And we'll go this way. This would be FC. Right? And the moment about X is going to be A is AX, AY, cosine 45 times F Z, is that right? A, Y, right? Let's see. X. So here we go. X, we got Y, X, and Z, X, Y, and Z, and MZ. And this is going to be a positive. And Z, moment about the Z, is going to be fx and a y. Somehow I got missing a z here somewhere. So cosine 45 again. And that's going to create a positive. You guys see what I'm doing there with the right hand rule? All right, so I've got, let me double check this. My, we've got a force going this way. We're going to rotate around that way. That's negative. I need to know this distance x, x across. I needed to know here. And this one here, mx, the moment about this is this distance, ay, ax, and then we had z, excuse me, that's az, there you go. That's where it's missing. So this is az, and this is f, y. There we go. All right, so I have to erase something here to fit something on. I'm going to stay with my right-hand rule because I'm better at that than I am with the cross product the other way. So I'm going to get rid of that section there.
There's no component of f in the y, is there?
That's what I'm, yeah, there's no, you shouldn't have any I, yeah. So this y component, so this should be 0, right? So this should go to 0, correct? And really, I shouldn't be putting the cosine. I should just say fx, fy, and fz, which we have from down here. That's a better way to do that. So all we're left with is that, our moment at A.
Wait,
minus.
are you ending up with no moment about the x?
What's that?
Are you ending up with no moment about the x-axis?
Yeah, which is what's confusing to me because we have no, we said that fy was 0, which doesn't seem right. We have I, j, so we should have something, there's no component in the y. So
That's true,
one of these is 0. So we have,
but it's not that one.
it's not that one. So we have x, a, right? I'm going to leave this. And then we have,
Why are you multiplying it by fy? Maybe I'm not clear on that part of the technique.
so really what I did was I broke this into components.
It's the f that's parallel to z that should determine mx.
We x, right? mx, distance z up, right? So we have z up.
What?
And then we go this way, which would be MZ, which would be FZ. Okay, so it's Y. This is backwards from the way we normally do this. This is Z, like that. There you go. That's why that's not 0. Excuse me. Times. Let's look at this one. So we have this. FY. That's Z. That's not right.
What about Y?
This is why it's confusing. We got actually there should be more. That's why. I'm running out of space here, guys. Hold on. So really we have two options. If we go back to our grid, there should be another. We have this vector around X. And then we have the other one. X, that one doesn't contribute. But when we go to Y, we have this. And then the other one might intersect. Nope, it creates. So we have. All right, I'm going to start from scratch here, guys, just to get this, get the vector correct. And I'm not going to leave the diagram up there anymore. So, what is F? We have, instead we have minus X, right? We have F cosine 45. Is that right? We have no Y. Minus F cosine 45. Okay. That's plus, right? Yeah. All right, let's do the, go back to the vector format, which is I, J, and K. We have R, which is, this is where the problem was, is I had a 0 in there. So it's A, and A, right? And it's, yeah. Is that correct? Jump in there. And then we've got.
What do you, because it's the moment about a line, right? Like not just the point. So where is AAA coming from?
That is, oh, that's not the distance. It's the distance we're doing in the moment at A. So we've got point F, which is at C. So the distance A, right? And the distance J is A. And the distance to in Z is 0. This is 0. And here we have minus F cosine 45. And then we have 0. And then we have F cosine 45. Okay. And then we put A minus F cosine 45. And then A and 0. Right. So this is 0 and 0, right? So we end up with I A times F cosine 45. And that is a positive. correct? And let's go with all the negatives. The first negative that we can do, here's I and J. We can go this way. So that's a plus because that's a negative. So we have F cosine 45, and that's a K. I like enough. 45. Okay. The next term, 0. And then the next term, J. This was, excuse me, I. Okay. And then J is going to be minus F cosine 45. And that's J. J goes on the other side. We end up with an I, a J, and a K. Which they have in some weird format there. And they end up with a negative J, which is what we have, some positives. Yeah, so we end up with the same answer. Their F, AF over the square root of 2 is the same as our F cosine 45. A and all R's there. That's the same. That's correct. That's moment A. And then we have to just implement the unit vector times each of these. So it's I times I, which is A cosine F cosine. You guys are making me walk through the mud here. And times the square root of 3. That's I, but except it doesn't matter anymore. That's a positive, right? And then the J minus, it's going to be A square root of 3 F cosine 45, right? And then we're going to have plus the K is going to be AF cosine 45 over square root of 3. So these two cancel out, and this is what you're left with. And if you just reduce it to what they have, you get the same answer. How was that for ugly?
I was going to say, if you're encouraging us to only spend, 6 to 8 minutes on a question, that was way too long.
Yes.
So essentially, you're taking the moment about A using the cross product from the origin, which is A, to the head of F, right?
So you're taking the moment about A by using the cross product of the vector A, B, and vector F.
Yeah, like you're first taking the moment about A, so you're taking the R vector that you used, AA0, is from the origin to the head of F, right?
Yes.
And then from there, you're multiplying it by the unit vector to project it onto RA.
Yeah. Correct. To find out what component is in the direction of AB.
Yeah, to get the right direction. Okay.
So how was that for painful? All right. Like I said, I don't like problems that don't have numbers in it. I think most people are more astute. I think a lot of this means that you have to carry all those variables with you the whole time. And that's why this is so painful. All right, let's go on to so I can tell you that there won't be any problems on determinacy. This just is reviewing what we did in that last lab. other courses place an emphasis on this. I included it because I wanted you to see it. It's nothing you're going to be tested on, but you should be able to answer these questions. Free bodies. You should be able to draw a free body. There might be a question or two about which is the correct drawing of a free body. Hopefully I don't need to overdo that, but. So these are asking you of all the structures are statically indeterminate except for which of the following. So basically they're asking which of these problems can you solve? And that hopefully should be really easy for you at this point, but like I said, not on the problem, not going to be on the final. And so that would be D. This one has is determinate but unstable. We have 3 rollers, so that is going to be unstable, so it's not going to be solvable, and that makes it indeterminate. This one here has too many reactions. It has 4 reactions. Each of those pins has 2. This also is indeterminate because it has too many reactions. There's 3 at the fixed beam, 1 at the roller. So this is the only one that's solvable, which is D. And so the answer is D. And this is a distributed load problem. I think they're asking you to solve for the reactions at B. And they've actually, they've broken it down nicely for you there. You don't have to do some of the legwork. Dave, also the thing about how long this is taking to do, this is me being rusty. Hopefully you guys are less rusty than I am.
I just think as a test taking strategy, if I hit that one with the cube and I was like, oh man, this is going to take, I would skip it, right? I would guess and move on.
Yeah, test taking strategy, multiple choice. Like I said, some of these questions, you're going to be able to look at them and you're going to be able to solve in less than 30 seconds.
Right.
Some of them will take long, but yes, you're right. I would probably have passed over that because they're all weighted equally. I would come back to that one. This one here. So all they're asking you to do is to figure out, they've given you the location of each of the loads of the, the uniform loads where the equivalent load is. So it's just a matter of solving for what F1 and F2 is in this case. So what is F1 and F2? Change to my screen. I'll share. So we've got what they're calling F2 and F1. So what is F1? Anybody remember the formula for an area of a triangle?
1/2 times base times height.
Yeah, half times 7 times, and how long is that? That's 1 meter long times 1. That's going to be 3.5, right? So we're going to have 3.5 newtons. And F2 is 3 times 1, right? We got 3. So, and they're asking for the reaction at B, right? So we want to know here. So if we're going to take a moment someplace, we're not going to take it there because it's not going to provide the answer for RB. So we're going to take the moment at A. And so we've got F1. And they even give us the distance. is times 0.33. And which direction is that? Is that negative or positive for a moment? Going into the board, right? Negative. And F2 also going to be negative. So F2 times 0.5. And then RB is going to create a positive moment. So it can be RB times 1. And that's all equal to 0. RB. And then you just solve for it. I'm not going to bother. I think you guys can figure that out. That's the methodology.
Rob, can you go back to that diagram real quick with the F1? So you just said it was area of a triangle. It was 7 by the distance or whatever, but is it right? Isn't that like a trapezoid? There's the bottom part.
So what we're doing, let me go back to sharing my. So what we're doing is we're breaking this load. This is what the load looks like, right?
Yeah.
Yeah, it's a trapezoid. So what we're doing is we're doing force 1.
Oh, I didn't see what they were.
Force
The
2.
F1 is the entire triangle, and the F2 is the entire rectangle. Got it.
Yeah.
Okay, thanks. Yeah, thanks.
Yeah. Sorry. So to skip over that. Yeah, this is real nice that they've done that. To be honest with you, a lot of people make that mistake when doing these kinds of problems. They try and make it just one force, and it really has to be 2. So here's a cable problem. This is sort of goes back to the early part of the course. You'll note right away, if you remember our lab, that T2 really is really can't be horizontal, but it is for the problem. So this, I'm sure you've seen this kind of problem several times. So what's the methodology here to solve for this one? This is more like particle statics rather than body statics. So there's no moments because we're doing particles. So some of the forces in the Y and some of the forces in the X, the only 2 things you got at your disposal. If nothing happens moment-wise. So we really can't solve X because we're going to have an unknown and an unknown. And we know that they're equal to each other, but we don't know. There's no way to solve that. So we have to start with some of the forces in the Y. So it's minus 50 newtons plus T1 times cosine 45. That allows you to solve for T1, whatever that equals. And so now we go down to here and we have T1 minus T1 times cosine of 45 plus T2. And we just plug that in there and we should get the correct answer. So Somebody fast with their calculator can do that. It's not too hard. P1 equals 50 over cosine 45. So if we were to plug that in, it would be any questions on that one? All right, so I'm going to take a quick break. I got to go to the bathroom. I'll be right back. Have a look at this next problem and see if you can solve it without looking at the answer.
All right.
Be right back. So the important thing to remember in all these pulley problems is that the tension in one piece of cord is always equal. They always make the assumption that they're frictionless. The rope doesn't weigh anything and the pulley doesn't weigh anything. So in that first one, or this problem here, what's going to be the tension in this rope here? It's going to be between the two, we're going to have 600 newtons in this one right here, right? We don't even need to worry about that one. We've got 600 going up to here. So now we can look at so this line here now, right there, this is 300 newtons. And then we're going up to the last pulley, And we had 300 newtons. And now it's going to be 150 newtons. And that's not an answer.
Yeah, I think you drew it wrong or we're looking at different problems.
I must have drawn it wrong. Hang on a second.
I think you're missing one pulley, Rob.
Okay. Hold on. So this first part right here, one, two, three pulleys, right? We got up.
There are four. There are four in the problem.
Yeah, well, there's this one up here. 1, 2, 3, 4. This first set here, I assume that this thing is not. So this is 600, 600. We agree that one side of this has got to be 600, right? 600, 600 down, this would be 1200. Is that right? And this would be 1200. Yeah, that's why it's an odd configuration. All right. Right here, what do we got? We said that this is 600, 600. Does that even work?
Yeah, I don't think that works.
Yeah, it doesn't work. That's why.
You
But somehow they've managed to, this has to be proportioned, which to me says that it's going to tilt, but okay.
So I think the way to approach it is like from the top, you've got so many T's. So
Yeah.
you've got 2 T's, 4 T's, 8 T's, and then you figure out that there's a total of 12 T's pulling on it. And then you can say 12 T equals 1200. And then
Yeah.
algebra. So 1
Yeah.
T is 100.
Yeah, I think you're right. I think it's better to start from that end.
Yeah, but why didn't his technique work?
Because right here,
It's not drawn right.
but it's not that it's not drawn right. It's just that you can't make the assumption that the weights, the two lines on the weight are divided in half equally. And that was my assumption, is that it was 600 and 600, and that's not true. So this is the, this is 2T right there, right? Going this way, 2T, and then this is 2T and 2T, which means 4T, and then this is 4T right there. Excuse me, this is 4T here. We have 4T, so we would then have 8T and 4T.
There we go.
So this was the problem right here, making this assumption. That is incorrect. So this is really 800 and 400.
Seemed
agree with
reasonable.
you
I
though,
mean, it's
Rob.
gonna put a moment on it.
It seems like it should be a fair assumption to say that both of those ropes have the same amount of tension in them from the start.
We're not not off by a factor of 2 anyways.
No,
Well,
because it definitely wouldn't be level.
Well, as soon as you tried to pull this, it's not going to be level, that's for sure. So, but yeah, so that's the difference, is this little segment here is 800 and this thing is 400. So that indeed, so Dave's approach from starting from the T was better. Friction, hopefully you guys know this equation. Friction is the force of friction is equal to the normal times the coefficient of friction. And in our case, we're always looking at the static coefficient. And here they're trying to determine what should F be in order to keep that thing from sliding down. So you notice the first thing they did was they changed the orientation of the axis to be that of the plane that they're evaluating on. They put X and Y at whatever that is. I think it's 3, 4, 5.
I have a question, Rob.
Yeah.
So what if you're just pushing down on a block? You're pushing directly down on a block on a horizontal table, and there's some coefficient of friction mu between the block and the table.
Talking about like,
Which direction is that? Huh?
you're talking about like this? Is that what you're talking about?
Do it again. Maybe I can't see you or something.
Oh, sorry.
Oh, I see your board. Yes. Yes, that's exactly what I mean.
Sorry.
So yeah, so
That's
which, right. So as we just stated, the force of friction is mu times the normal. So which direction is that force going in this diagram?
That is a really good question, Jason. And the answer is it's not. So, because we're not, if we were trying, well, the friction that it would take to move that would be F friction, the friction, let's call this friction force right there. To move, called P, and the friction to move this, F, would be mu S times the normal, and the normal would be equal to P, and we call this W, plus W, right?
Uh-huh. So it's
That
really
would be
the
the
force
friction. That would be the force to move it.
to overcome the friction.
Right.
Yeah.
So this
Okay.
force is, you know, the amount of force to move it is going to change. But is there any horizontal load on this now? You know, if we don't have F and we're just sitting there like this, you know, there's really nothing, there's no friction force really happening.
There's really no friction force at all. Yeah.
Right. So it's not moving. So
Okay.
let's go to the problem. That's a good question. So we've got this. And this is 5. Which one's 4? Which one's 3? 4, 3. And we're trying to determine F. And we've got a weight. And then, of course, we also have FS right there, right? And X, Y. And so the best thing to do is to break W into components in this new orientation. So we've got W, what we'll call Y, and WX. Clearly, we need to solve for WY to find out what the friction, what the maximum friction force can be. And that's going to be 4/3. This is the part where I get a little confused. So this is going to be over 5. So is it over 3 or is it over 4? It's going to be over 4 times, what is the weight of our thing? 250 kilonewtons. WY equals 200 kilonewtons. So now, what is Fs? And be the, if we were to do the sum of the forces in the Y, we would have WY minus WY plus the normal. Normal equals WY. So we're going to have WY times the coefficient of friction, right? And that should be, they give us the coefficient of friction, 0.15. 0.15 times 200. So that's going to be what, 30? All right, well, let's do the sum of the forces in the x direction. And so we've got Wx which is, what's Wx? Minus, should say minus Wx plus Fs plus F. Now we've got 150, so we've got minus 150 plus Fs, which is 30, plus F. F equals 120 kilonewtons.
Rob,
Is that an answer? It's available? Yes. E.
Rob, can you explain why the force of friction is going in that direction? Wouldn't it be going in the opposite direction of the supposed force?
Yeah, so what's trying to happen here, if we just remove this here, the way that this block wants to slide is this way due to the weight, right? So the friction force is going to be resisting that. What we're trying to determine is how much force here do we have to add to keep it from sliding? So we need to add in this direction to keep from sliding. Otherwise, if I drew Fs the other way, that would mean that it was adding to the sliding problem.
That would be a maximum force we could apply before it begins to slide upward.
Yes. Yeah, so F would end up being negative in that case. But the whole reason really is that if you just look at it like this force friction has to be acting that way in order for that block to be static.
Okay.
Because it has to be opposite direction of Wx. It just turns out that in this case, Wx is greater than Fs. So here we had Wx 150. Here we determine the maximum friction force that we can get here is 30. So the question is what does F need to be in order to keep it all static? Okay, on to trusses here. You will not be quizzed on what kind of truss you're looking at.
Haha.
I'm not sure why this is in the review, why you would care whether it's a how, a fink. I mean, that's nice to know, but it's not really relevant. So what they're asking you to do is to figure out the force in member CD. If you remember about trusses, that they're made up entirely of two force members and that all the pins are frictionless, the beams are weightless, otherwise it wouldn't be two force members. So you can only either be in tension or compression along the line of the truss member itself. So That's kind of the definition of a truss. And they've already decided there, and you could do this through the method of joints. You could work your way through. That would be fine. But I think the method of sections for solving this problem is significantly quicker, which is what they've chosen. Does anybody think that they would solve this by the method of joints?
Nah.
Yeah, probably not, right? Now they use some trickery here to solve this. I'm just going to draw the section that they've done. Let's go. And again, we make the assumption, and there's a load right here, 2P. And this is RA. And this is FCE. And this is the one we're looking for, CD and FBD. So normally, we would just solve for the reaction, right? Did they give the reaction there? No. So we have to solve for the reactions anyway, at some point here. So I'm not going to draw the whole thing there. You can look at the reference. But what we want to solve for is RA. So we would take the moment at B. So if we took the moment at B, we would have RA times 3L, right? And then we would, and that's going to be a negative moment.
How are they proposing they got RA?
What's that?
How are they
They aren't. They're assuming you solved it, which is what I'm doing right now.
They're assuming that you solved it.
Yeah. So you have to solve for the reaction, and that's usually a fairly standard core, you know, for a truss problem. So then we've got 2P times 2L, and then we've got plus P times L equals 0. RA equals 4PL, 5PL, 5PL over 3L, right? And the L's cancel out, so RA is 5/3 P. All right, so now we can start to solve for this. The easy answer here, so let's just say 5/3 P, oops, 5/3 P. So if we look at this problem here now, we know RA, we know this load. To me, what I would do, since this is the only component with a vertical component in it, would be to solve for some of the forces in the Y. And that would be 5/3 P minus 2P plus whatever that angle is, that's going to be 4 over 5 FC, whatever this is, T. We're going to call it TCD. I don't like F. And thus, what do we got? Do that right? Going to be 6. This is 1 minus 1/3 P, right?
I agree.
So, and that plus 4/5 P. P is going to be equal to 4/5 P is equal to 1/3 P. P is 5 over 3 times 4. Did I get the right answer?
Yeah, looks like it. 5/12 P.
Yep. Well, there you go. So yeah, you got to solve for the reaction first. Okay. All righty. This is another truss problem. What are they asking for? Reaction force at A. This one's actually easier than the last one in some ways. This one is only a one-step problem. So it's just a matter of doing what in this case?
Moment B, and then you'll get reaction A.
Yeah. We don't even really need the whole truss arrangement. Really, it looks like really it's just 3 loads, right? On a beam, that's really all we're solving for. We've got 2,000 and 3,000 and 4,000. And the hardest part is determining what their distances is. So if they're just going to do in half. So this is 3.5. This is going to be 10.5. And that one's going to be, I should have done from the other direction, shouldn't I have? Yeah, should have done it the other way. Anyway, you get the idea. 14, 17.5. So, A, B. You just take the sum of the moments at B. I'm not going to go all the way through this. This is pretty straightforward. So the whole idea is to just, you're looking for the reaction here, take the moment at the other side, and you'll get it. Note that they've drawn this as determinate. They have two reactions here. Not that we're using the horizontal one, but it's there. And the roller, they didn't draw it as 2 pins, which is nice. That, ironically, is the last problem. So do you guys have any general questions or specific questions? Any questions, really? So there weren't any frame problems in this test, or in this, I shouldn't say this test, in the examples that we just did. Frame problems typically are time consuming, in my opinion. I'm sure there's going to be at least one frame problem on there. So be forewarned. If you have any questions about frames, as always, the biggest problem with frames to me is drawing the free bodies correctly so that all of the points, when you draw the individual pieces, add up to the entire body free body diagram. Make sure that all your bits and pieces, your negatives and your positives, add up, and make sure you keep track of them. That is always the big trick in any frame problem, is making sure that the individual members, when added together, equal the same free body diagram as the entire body. If there's no other questions or anything, we're all free to go. I'm happy to stick around or not.
Rob, I have a question about in the pulleys section.
Yes.
There's the type of pulleys like fixed sheave, free sheave, ordinary pulley block, and sheaves. And all of those seem fine to me except for the last one, differential pulley block.
Is that in this? Go back and look. I see what you're saying. Hold on a second. You're talking about this diagram?
Yeah. The one on the right.
Yeah. That's not going to be on the final there, that differential pulley block. So what they've done there. What's that?
Would it be?
What's it all about?
Would it be on a? Do you think do you recall if they had problems like that on your FE?
They might be on the EIT, yes, but not certainly for this class. What's going on there is, of course, you have different diameters. So the rope is going to move at different rates and provide different mechanical advantage. I don't quite understand their diagram. It looks like one.
Yeah, neither do I.
Looks like a continuous belt to me.
Continuous.
Yeah, it's one cord.
So I'm not sure what's going on there. It seems to me like you would need to break that cord somewhere, but.
Okay.
It exists in the fourth dimension or something.
Yeah.
Yeah. Sorry, Maria, I really can't answer that one because I don't understand their diagram.
Yeah. Okay. Thank you.
We certainly won't, like I said, this won't be on the test. Yeah, that's kind of weird. So if there's nothing else, I will see you guys a week from today. Like I said, I'm mostly there to answer questions. That will be my entire role. I don't think that you'll need to log on unless you have a question to ask. I think it would be easier just to log on early, just so that it's running in the background, so that if you have a question, you don't have to wait for the link to go and be frustrated by any loss of time that way. Also, I will be having office hours next Wednesday. And of course, you can always email me any questions. And if you want, to meet separately, we can always set up time to meet separately. Like if you email me and say, hey, I want to get together before Wednesday or after Wednesday or some other time, please do that too. You guys have been a pleasure. I wish we had done this in person. I think everybody learns better, including me, in person. I think I teach better in person too, but that's debatable. But anyways, you guys have been a pleasure. I really have enjoyed you guys. You guys are a pretty good set of students. I have no doubt that you guys will do well in the future and on this final exam.
Thank
Thank
you, Rob.
Yeah,
Thank
thanks,
you
Rob.
so much, Rob. Much appreciated.
Rob.
Take care.
Okay. Take it easy.
Thank you, Rob.